Hello, welcome everybody. Thank you for your time today. I'm glad that you could join us for this webinar, which will introduce you to our Chirascan family of circular dichroism spectrometers and some of the applications where they can be utilized. Just for some background detail, Applied Photophysics was founded in 1971. It's headquartered in the UK, which is where we manufacture the Chirascan series spectrometers, as well as our SX20 range of stop flow spectrometers. Recognized as the gold standard in monitoring absorbance and fluorescence during fast kinetic reactions. My name is Mark Neglia. I'm president of the Americas, and I manage the team here in the US office, which consists of sales, service, applications, and customer support personnel. I'd like to welcome everybody from around the world that has chosen to spend this time with us today. I would ask that you please enter any questions that you have during the presentation in the message box. We'll try to answer as many questions as we can as possible at the conclusion of the presentation. If we do not get to your question within the time allotted, we will follow up directly with the email address that you provided. There will be a short questionnaire at the end of the presentation. We ask that you participate. Please take a few minutes to answer those questions, as they'll be helpful. Also, this webinar is being recorded, so if you weren't able to attend or have to log off later, earlier or something like that, we'll be sending a link to everyone that registered so that you can be able to watch it at your leisure within the next couple of days. With that, I'm very pleased to announce our speaker today, Dr. Frank Wan, who's one of the application scientists here in the US. He works out of our lab facility in Beverly, Massachusetts. Frank holds a PhD in biochemistry from Florida State University, where his work included the biophysical characterization of RNA structure and function. He's an expert in the applications of circular dichroism and stop flow kinetics. And with that, I'll turn it over to Frank for his presentation.
Good morning, everyone. Welcome to Applied Photophysics webinar series. So today, we're going to introduce Chirascan CD spectrometers. And my name is Frank Yuan, as introduced by Mark. And I'm one of the application scientists at Applied Photophysics, located in the Boston, Massachusetts facility. So as Mark says, we were founded in 1971 in United Kingdom. And in 2004, we introduced the first Chirascan spectrometer series. So this was the highest performing CD spectrometers on the market. It used all digital electronics and it used a unique dual polarizing prisms. In 2006, we introduced Chirascan V100. It is still the first and the only CD spectrometers with solid state detectors. And we're going to talk about dual polarizing prisms and solid state detectors a little bit later, why they are unique, why they are very important for CD measurements. In 2011, we introduced fully integrated advanced robotic system for the Chirascan. You can run up to 4 96-well plates at once, so you increase your throughput much higher. So this is just a graph showing the publications using Chirascan CD spectrometers over the years. After the introduction, you can see the publication numbers increased quite dramatically. And with the vaccine and antibody development in the spotlight, we expect the Chirascan spectrometer is going to be more utilized in the coming years. Today, we're going to put this presentation into 2 parts. The first one, we're going to introduce the innovations we'll put in the spectrometers, why it can be more accurate, why it is more sensitive and more reproducible. And then the second half, we're going to introduce 2 case studies, which will showcase the capabilities of the spectrometers. So very brief technical introduction about circular dichroism. What is it and what it can be used for? So all the lights are polarized, is electromagnetic radiation. You can view as vertical and perpendicular linear polarized. When you overlay perpendicular and linear components together, you would get, and with a quarter of phase shift, you would get circular polarized light. And this circular polarized light can be right-handed or left-handed. And circular dichroism, CD, is basically an absorbance method. It measures the differential absorbance of the left-handed polarized light and right-handed polarized light. And if the left-handed polarized light has more absorbance, you would get the CD signal in the positive range. Otherwise, you would get negative range. If you have the same absorbance for both polarized lights, you would get 0. So it is going to be CD uninformative. So because it's a absorbance method, it requires absorbance. So a chlorophyll which will absorb light, and then it requires chirality. Chirality is the molecule which can be superimposed, is a mirror image, but they cannot superimpose to each other. So these two requirements is the technical foundation for CD spectrometry. So CD can be used in many different research fields. So protein, nucleic acids, nanomaterials, and like metal complex, and so on. So today we're going to focus on protein science. Protein science is one of the major application areas for CD applications. And CD signals from proteins are from, we can divide it in two different regions. The far UV range, which is from peptide carbonyl bonds. So the peptide bond is all through your protein chain. And it can be at pi to pi star transition, which is around 190 nanometers, and N to pi star transition, which is 210 to 230. So those are in the deep UV range. And then we have the near UV range, which is from the 3 aromatic amino acids and disulfur bond. And traditionally, people knew there are a lot of information you can get from those range, because those aromatic ranges can be in different environment, different hydration, different hydrophobicity, and so on. So it's very useful to detect the tertiary structure of the protein. But traditionally, it's difficult because the signal is much lower. The intensity is much lower. So you would have to have higher concentration, and also a lot of noise as well. So we increase the sensitivity so you can get meaningful data in those range, and you can have those signals to give you information about the tertiary structure. So disulfur bond, phenylalanine, tyrosine, and tryptophan. So CD applications in protein science. So the first one is the secondary structure. You can gain insight. This is an example of a protein CD spectra, mostly alpha helix dominated protein. So you would get signature peaks and valleys for alpha helix. And some of you may have some question. What is the blue line? The blue line is a unique feature for our APT detector, the solid state detector. It is the absorbance data. It always comes with your CD data, and this absorbance data is very useful. It's very accurate. It is very useful for internal normalization. So concentration normalization, you don't have to match two proteins concentration exactly the same. You can it can be used for normalization. And this is another example for the secondary structure, which is a beta sheet dominated protein. You can see the peak and the values are shifted and the shape are different. So this this will help you gain insight into the secondary structure of your protein and tertiary structure. So this is just an example. I would imagine for many of you guys, you may not see this often. The reason is because for conventional CD spectrometer, it is difficult to detect whether those are signatures, peaks, or they're just noise. So we're going to demonstrate with Chirascan spectrometers. Those will give you meaningful, reproducible, and reliable data to gain insight into the tertiary structure. So Chirascan Innovations, we're going to introduce the Chirascan, the hardware and software innovation. But before that, why we're going to do that? It's because we want limit, decrease the sample consumption. Sometimes your sample is very precious. It's difficult to purify or difficult to manufacture or to make. So the lower concentration, the better. So you can use less sample to get more sample measurements and so on. So this with more sensitive spectrometer, you can use less sample to get the same signature peaks. And sometimes your sample may be photolabile, which is not stable under intense light. So if you decrease the collection time, it could be helpful. So with the higher sensitivity, you could do that. So with much shorter collection time, you still get signature peaks. And also it can decrease your experimental time, right? You don't have, like if you have experiment, you have to run 5 hours. Now you can only run 1 hour, you can finish the experiment. So that's why we put so much effort to increase the signal to noise, so you can have better results. So this is just a comparison study done with our partner university in Germany. So this is near UV CD spectral from a protein. So you can see different peaks over here. But with the conventional latest generation CD spectrometer, the peaks are not well resolved. So that's a big difference. And with lower concentration, so the concentration is 3 to 4 times lower, we can still resolve the peaks, but there's very little peaks there. And with even lower concentration, you can still see the peaks. But for the conventional spectrometers, you can see other peaks coming up. You don't know whether that's signal or noise. So that's a dramatic difference you can see. So why is that? Where are the what are the innovations? So the first one is we want to ensure the wavelength is accurate throughout the region. We just here we just show 180 to 300 nanometers, but we actually calibrate from 180 to 1100 nanometers. The whole range. We use a optical-based device. It's called Dichroism. It's patented device used exclusive by us. So it is optical based. There's no chemical to prepare. There's no degradation over time. You can calibrate the whole range continuously with this device. And traditionally, and for most, not only CD spectrometers, but other spectrometers, you would use standard chemicals to do point calibration. And generally, you don't use hundreds of points to do calibration. Secondly is those chemicals are less stable, and it requires a lot of scale to make it to work properly. So this is the innovation for the wavelength calibration. And for signal to noise ratio is the most important parameter for a CD spectrometer. And signal to noise is positively related to the intensity of the light which hits your sample, and also the quantum efficiency of the detector. And for other parameters, they are sample dependent. So for hardware, we want to increase the intensity of the light. We want to increase the quantum efficiency. Intensity light is increased with our dual prism setup. So those prisms, both of them not only select the wavelength, but also the polarizing light. So the light going through your sample is very intense. Is the highest on the market at this moment, and the absorbance, the CD detector quantum efficiency is much higher for the solid state APD detector as well. So this APD detector, we have a graph showing the dramatic difference. So quantum efficiency is the photon. So your photon hit the detector, and then this photon is converted into electronic signal. And if you have higher efficiency, that means the most signal is getting captured by the electronics. And if it's lower, so for PMT, it's about 20%, but for APD, it's much higher, like 40 to 60%. In the lower range is even higher. So this increased the signal to noise ratio quite a bit. And then because we use the avalanche photodiode detector, ADP detector, it is because the gain, so the gain is you have the photon to the signal. This gain is long, so we can get a very accurate absorbance. But for PMT, the gain is unreliable. You know, at different time point, you would get different gains. So the absorbance data, you can still get the absorbance data, but it may not be accurate, yeah, for a lot of instances. So this is just added benefit of the solid state detector. You always get absorbance data together with the CD signal. So other unique function includes AMS system. So if you have experience with CD spectrometry, you will know it requires nitrogen purging as well as lamp stability. It takes sometimes hours to purge the system and make the lamp stabilized. But for this system, you can schedule it. So whenever you schedule it right, it is ready when you are. And the second unique feature is we develop a higher order structure analysis software, so it can analyze the higher order structure for you. And then there's a global 3 software to analyze multi-wavelength spectroscopic data. You can find multiple melting temperatures and enthalpies and so on. We're going to use a couple of case studies to showcase those software, and they come with the instruments. And the Chirascan spectrometers are very versatile as well. You have a whole range of accessories. Those are just some examples. So if you want to run 6 samples at once, you can use the 6-cell turret. If you want to measure CPL, you could just put our device there, and by pushing a button, you can make the CD spectrometer as a CPL spectrometer. And you can also run solid state sample. You can monitor the pH. You can monitor the fluorescence. You can measure the magnetic CD as well. So there are many more. And if you have any questions, or we would send you more information about those accessories. Now let's go to the first case study, is to study the protein stability with nanoparticle. So this is done with a collaboration with a leading research university in Germany. So the objective were to characterize the secondary structure of the proteins. Those proteins are called enzyme 1 and enzyme 2, and then by expose those proteins to nanoparticles, want to find out what's the impact on the secondary structure as well on the protein stability. So those nanoparticles are very relevant to vaccine and antibody development because they are commonly used as adjuvant. So those nanoparticles is made of aluminum oxide. So now let's look at the data. So enzyme 1 is the CD signal is like this. So CD spectrum is like this. By analyzing it, it is alpha helix dominant protein. So for enzyme 2 is so the CD signal, the red line is like this. So it's consistent with a distorted beta sheet. So those are the secondary structure features for enzyme 1 and 2 before exposing to nanoparticles. And then for enzyme 1, after nanoparticle is added to the sample, you will see there's little change for the secondary structure. So we conclude a minimal effect on the secondary structure of those enzyme 1. But when you look at enzyme 2, the structure is very different. So this is the control. This is after nanoparticle was added. So they are very different. So the secondary structure of enzyme 2 were changed dramatically, as you can see from the CD spectrum. So now we are doing a thermal stability study for enzyme 1 and enzyme 2. So enzyme 1 data were not shown. They didn't show any difference. So this is enzyme 2 without nanoparticle. So this is the thermal melting data we got, and we fit with the global 3 software. We get the melting temperature as 45.6. And let's just put a few moments on this this data representation. So for most melting study for the CD spectrometers, you would choose a wavelength, but this one we choose the whole range, right, from 190 to 250 nanometers, the whole range. Every temperature we get a spectrum, not just a point. We can do that. So the Chirascan can do that is because the detector is fast. It's able to scan the whole range, within the temperature, also the time. But for the traditional PMT, it's not fast enough. You would only choose a few points or 1 point, and so that's also we developed the thermal study, so you can always finish one melting study within 1 hour, about 1 hour. Sometimes if you have a longer range, you would use, for example, 20 degrees to 90 degrees, you will use 71 minutes, but most of the experiments can be done within 1 hour. And this is a 3D representation of this data using the Global 3 software. So you can see there's 3 dimensions to show this data. So this is before nanoparticle were added into the sample. This is after. Same process. We go through and then we fit with the Global 3 software. We find the melting study is 2.9 degrees higher. So that means the nanoparticle gave more stability to the enzyme 2. So that's the case study number 1, so protein study. So just enzyme 1 doesn't have much change for the secondary structure. Enzyme 2 has profound change for the secondary structure, and the enzyme 2 was stabilized by the nanoparticle, but not enzyme 1. The data will not show. So this is just showing the power of the APD detector. You can do the whole range scan, and also within a reasonable time. Now let's move on to case study number 2, biotherapeutic stability study. This is more relevant for the tertiary structure. So the objective, so industrial partner. So for most of our study, industry partners generally don't want disclose their name. They just say, oh, it's just an industry partner. You can maybe use our data. A lot of times they actually don't allow us to use their data. But because our data was so impressive, they actually allow us to use their name as well. So this industry partner is Boehringer Ingelheim, and so they want a second opinion on some compounds they are under study. So in-house, they had a lot of complementary methods, so like a mass spec or other methods. So they got conflicting results. So this is the samples they have. So mono antibody 3, so MAP3, MAP4. So they use mass spec to do deamidation method. So deamidation means whether it's degraded or you can see it's modified. So those samples were deamidated 16%. So MAP3 16%, MAP4 13%. So put this number in perspective. This is a higher deamidation, this is lower, but they have some other method. They found out 16% deamidation actually had less impact on the structure and the function than 13%. So they are not very sure. So that's why they ask us to do some CD measurements to see whether it can confirm or it can give them assurance. And so after this sample run, they not only purchase one of our Chirascan spectrometers, they also are very happy, so impressed. They are very happy to share those data with us, so we can share with the audience. So this is the study, MAP3. So we run the near UV spectra for the MAP3, and those they look very. It looks like that's 19, but actually it's 10 repeats. 5 for the original non-deamidated sample, so just original sample, and then 5 is after deamidation, 16% deamidation, and they overlap pretty well. But are they different? It's very difficult, especially there's a very small difference. So we use the House analysis, higher order structure analysis software developed by us to do the statistical analysis using FDA approved range, so accepted range. So this is the original samples, so within the range, and this is after 16% deamidation. Most of them are falling into the accepted range. So we conclude there's not statistically different with their tertiary structure, because this is in the near UV range. So those peaks are from the aromatic rings and the disulfur bond. So not much difference after 16% deamidation. So that's for MAP3. For MAP4, we went through the whole process, the same process. So six samples before deamidation, 6 samples after deamidation, 13%, right? So put that number in perspective, 13%. And they look very overlap pretty well as well. That's a little bit difference here. But after going through the House analysis software, we found out clearly after deamidation, 13% deamidation, the tertiary structure was altered significantly. So it's outside those accepted range. So that means their suspicion was right. Even 13% deamidation will have much higher impact, bigger impact on the tertiary structure. So so this is the power of reproducibility, right? So if there's anything like a little bit change, you would find a significant change. So you have to have your spectrometers to be really reproducible and really sensitive, because those signals are very, very little in those the near UV range. So that's the conclusion. Secondary structure, we didn't show them. There's no significant change. for deamidation for MAP3 and MAP4, but for tertiary structure, 16% deamidation, same that not to change MAP3 tertiary structure, but significantly altered MAP4 tertiary structure. So those results confirmed by the host analysis. We designed a software using FDA approved guidance, and so that's for case study number 2, and this would conclude today's webinar as well. And I welcome your questions or comments. Thank you very much for your attention, and you are going to get one of the copies of this presentation as well. And this webinar is also recorded, so you will get an email for the recorded address as well. Thank you for your attention. All right, so for the so we got a few questions. No, that's we got a few questions about accessories. So there's accessories. So asking, can you expand more about the accessories? And now let's go back to the accessory page. So the accessory, we have a line of accessory. So as we discussed, we have higher throughput accessory. We have higher added capability accessory CPL, and we have magnetic CD accessory and solid sample holder accessory as well. So if you have any specific needs, we can talk. There are quite a lot of accessories available for the Chirascan spectrometers, and you can use those for your research. Okay, there's one question about what's special about the APD detector. So the APD detector, as we discussed, the APD detector can have higher quantum efficiency. So the quantum efficiency, as I discussed a little bit, is the conversion rate from signal photon to the signal in your electronic, so the collection software. So the APD detector cover a much longer range. You can see PMT generally does not work after over 800 nanometers, and those range could be useful for nanomaterial development and other studies. So this is the first one. The second one is the efficiency is much higher. The quantum efficiency is much higher than the PMT. And the third one is APD detector is solid state. So we know the gain. So we can actually get very accurate absorbance data. But for PMT, the gain is not reliable. So it could you get the absorbance data from your spectrometer with PMT detector, but it may not be useful or reliable. So that's about APD. So the nitrogen gas. For CD spectrometers, because we use very high intense, especially when you do protein CD measurements, you would use very high intense UV light to do the measurement, and the UV light is able to have a chemical reaction with the oxygen in the air. It will form ozone. So the ozone is bad for our health. It's also bad for the electronics, for the detector, and also it has very strong absorbance in the UV range. So basically, it's bad in 3 different fronts. So we have to purge it out to get a better signal, as well as for safety, and it can damage the lamp and damage the optics. So we have to purge it, and it takes some time to do the purging. So there's a question about the value of secondary structure fitting software. So there are many software, most of them are free. You can use to fit your secondary structure CD signal into the software, and then it will give you the percentage of secondary structure elements, like alpha. What's the percentage of alpha helix? What's the percentage of beta sheet, and so on. So it is quite useful, especially traditionally if you don't have a good reproducibility to give you a number. But there's complication about the fundamental method. It's there are many different elements. As you know, if you have just alpha helix and beta sheet, you could get very good fitting. But there may be some other different segments, different elements, like distorted beta sheet, as we discussed a little bit for enzyme 2 in the case study number 1, and also other different elements. So it could be very difficult mathematically when you have many, like over 20 different secondary structure elements. Furthermore, every model has a reference bank, right, data bank, and you have to use the reference to do the fitting, and every software would rely on one unique set of the reference, and the reference could be distorted, could be incomplete, and so on. So it is if you want to get this absolute secondary structure percentage, it is very difficult, and if you use that a lot. But it is useful, as I said, and also just keep in mind, CD spectrometry is very powerful to find out the difference. Like for the 2 different case study, the first one is the melting study. The melting study is actually the difference, right? So you find a different difference between different temperatures. And for the second one, the stability, you would find a different condition, the difference. So it's very powerful and very useful to find out the difference. And it's not absolute, right? Not like NMR or any like X-ray crystallography. You find the exact structure. So it's so that's always keep that in mind. And but CD has its advantage is the sample preparation is much easier, and the consumption is minimal, and it can be recovered for a lot of sample. You can actually reuse them. You can actually recover the sample after use it. It's non-destructive, destructive, and it can be reused. So there's a question asked, why not 223 and 209, but not 222 and 208? I'm not sure about the question. Maybe it's the wavelength for different secondary structure. Why not? So this is the question. The question asked, why not 223 and 209? Why not 222 and 208? So those are the I think the question is directed about the secondary structure or peaks or valleys. So those are a little bit, maybe a little bit question about why is a little bit difference in the wavelength. So this we can discuss more afterwards. Okay, so there's a question says, will structure changes be absorbed if a ligand binds while working with APD? I think the question is with the new detector. Can you detect the structure changes after for the ligand binding? Yeah, the question is the answer is yes. And if the ligand, so there are a few conditions, right? A few scenarios. If your ligand is CD uninformative, that means there's no CD from your ligand binding. It's very straightforward. You measure your protein sample by itself, then you add your ligand in and observe the change, right? So if there's any change, that means the ligand change your structure, whether it's secondary or tertiary structure. This is the easy part. The a little bit more complicated part is maybe your ligand, maybe it's two different protein. You have protein-protein interaction. You put in the ligand itself has some CD signal. So this one you have to do a control, right? You have to measure your protein and your ligand separately, then put them together. Then you can mathematically calculate whether there's a change. So that's a process of doing that, and we have many users using those kind of applications, and it is totally doable. So there's a question about what are the path lengths for the cuvettes. The path lengths of the cuvettes. So we have the manual system, the cuvette. Path lengths can be as low as 0.1 millimeter, so very thin cuvettes, and then 0.5 up to 10 millimeters. So those regular square cylinder cuvettes, that's the highest, up to up down to 0.1 millimeter. So when you have the Chirascan, you would get 0.5 millimeter cuvette, as well as 10 millimeter cuvette as standard. But you can purchase down to 0.1 millimeter, and then anything in between, something like 0.2 millimeter, 1 millimeter, 2 millimeter, 5 millimeter, and so on. And for the automatic Chirascan Q100, and we have the standard the 0.1 millimeter up to 10 millimeter as well. So yes, so that's a big range for that, and the range for the path length is actually very useful. So a lot of times you don't have to change, you don't have to dilute or concentrate your sample, right? If you change the path length, for example, if you measure your protein with 1 millimeter path length, you find it's too diluted. What are you going to do? You're going to use maybe a lower path length, maybe 0.5 millimeter path length. Basically, you dilute the sample 2 times, using just by changing the path length. And the other way around as well. If you find your sample is too diluted, you can use higher path length. So that's the beauty. That's kind of the method advantage for the CD. You don't have to do dilution on the concentrating for a lot of measurements. So this would be the last question. And if you have any other questions, please send us an email. We're going to send you the response. We're going to keep in touch. Thank you very much. and hope you enjoy the day, and thank you for your time.